Good morning, all of you. One more session for our examples, and in this session, our topics would be resistor networks and also the EMFs. Few models will cover for our CET and NEET. Remember, we're not doing any examples, or even for that matter, even we're not doing our concepts to the levels of JE. These are very specific sessions for our CET and NEET flash. Look at this first example. 4 resistors in network and asked you to find the effective resistance across the open terminals AB. Remember, what do we mean by open terminals? Yes, they are the terminals across which PD is applied. Same examples can be given including a cell and can be asked you to find currents and voltages, which we did earlier. Now we are simply finding effective resistance. Now to find resistance across A and B, look at how to find whether they are in series or whether they are in parallel. Our rule was undivided current will be series, common potential points will be for parallel combination. Now here, can you find any such series or parallel? Because it's a simpler one I have started with. You see here, this C and D, they are at same potential. Why? Because any 2 points, supposing between 2 points there is one component, any component such as resistor or capacitor or anything like that, then there exists a PD. The 2 points will be at different potentials. But now here you find C and D only a conducting wire. Generally all conducting wires we consider to be of negligible resistance. So C and D points are same. Therefore whether I say A between AC or between AD, it is one and the same. C point and D points are the same. If I tell you that, similarly now BC and BD will also be the same. That is to tell you that 6 ohms is across AC and this 12 ohm is also across AC. Got the point? 6 ohms is across AC. This 12 ohm is also across AC. This is the 6 and 12. See? 6 and 12. I am rewriting 6 ohms and 12 ohms are in parallel, because these are connected between A and C. So if I call this point A, this is what is C point, and this is nothing but D as well. There is no distinction between the C point and D point. Similarly, you apply the same principle between B and D. Between B and D. So these are 2 more resistors which you will find in parallel. I think now you can make it out how this network is redrawn. So this is 6 and 12, this is 7 and 3. So this is now gives us to 6 and 12 parallel, R1 R2 by R1 plus R2. Use the rule, 6 and 12, you will get it as 4, 7 and 3. 7 into 3 by 7 plus 3, it will be 2.1 ohm between the terminals AB. Now, final answer would be this 6.1, because it's a series combination of 2 resistors. Therefore, now final answer is RAB. I am writing the final resistance or the effective resistance across AB as 4 plus 2.1. 4 plus 2.1. So this is 6.1 ohm, the effective resistance. Like this. Got it? Now let us do one more example. In that example, we would like to give a concept of common potential points. Common potential points. Now see, this network, here it is given to be all identical resistors. 6 resistors I have shown in the network. 6 resistors and all of them are identical. All of them are identical. In fact, this example I need not use common potentials also. Let me do it by redrawing the arrangement only, so that we will continue the concept of common potential points for the next example. See, this is redrawn. How it is redrawn? Look here. Supposing it is only the question of bending of the wires. It is only the question of bending of the wires, right? Now redrawn. Look at the points A and B. Look at the points A and B. B point, right? Is that okay if I write B? And is that okay if I write it as A? Is that okay? See? This is no distinction. If this is A, this is also A. If this is B, this is also B. Likewise. Then these two resistors, R and R, parallel, because these are the points across which two resistors are connected. And here also you will find, yes, these are the 2 points across which are, again these two resistors are parallel. So this is R by 2 and this is also R by 2. So if I redraw this, yes, this is your point A and this one is, yes, R by 2, yes, this one is R. And this one is also R by 2 and this is R. Now you see, redrawn. These are the terminals A and B. Now R and R by 2. Across AB now you see. Across AB now you see R by 2 and R series. Here also R by 2 and R series, 3R by 2, this one is also 3R by 2. Therefore now, finally we got one simple parallel combination, each of 3R by 2. So two resistors, identical, each 3R by 2 and it is parallel. Therefore what is the final answer? It is 1 by 2 times 3R by 2. Because identical resistors, n number, parallel, R by n. I have used that identity. So it is 1 by 2, each of 3R by 2. So the answer is 3R by 4. Answer is 3R by 4. In fact, this can be solved in other methods also. I am showing the very common method I have shown. This can be done even in 2 lines. I am not showing that here because it can be written as an equivalent of Wheatstone network and we can solve it in 1 or 2 lines. But I have shown you the general method. See this example. A network is given. Again, asked to find resistance across AB. Resistance across AB. Actually, this example we can solve based on our idea of Wheatstone network. Same Wheatstone network only, but for a particular concept I am giving the other way. What is the concept? Is you will find first it's a complete symmetry, right? There is a mirror symmetry, right and left symmetry that you can observe between the points A and B. Therefore, whatever current, supposing if this is what is current I, that's the splitting when takes place. The splitting when takes place. Let me call these node points, nodes as C and D. Then, because of this symmetry, what you observe, this current divides equally in the branches of A, C and A, D because of same resistance. We know whenever current splits, it's always in the inverse ratio of resistance, same resistance, same current. Therefore, if this is what is I1, this is also I1. And this current will be I2 in this branch, like that. So similarly, here also you will find the same 2R and 2R. Therefore, what is that you observe? This AC, V across AC, use V is equal to IR, same current, same resistance. Here also VAB is equal to, VAC is equal to VC, VAD. Yeah. Now see, VAC is equal to VAD. That is C and D point become points at same potential, which we are calling common potential points. C and D now happens to be common potential points. Therefore, no PD means no current in that branch. Therefore, all those resistors in that branch becomes ineffective. Of course, same may be the rule for the Wheatstone network also, but this method will help us in some other examples. I will continue with one or two more examples. There, this identifying common potential points. Here in this example, I made it easier. In next examples, we will find that common potential points will give us a simple solution, right? Otherwise, it is also nothing but a balanced Wheatstone bit that we can see afterwards. VAC is equal to VAD. Therefore, now this is redrawn, our new and final. This is 2R, and this one is also, this branch is 2R, and now this branch is R, and R is 2R, and of course one more branch here. Yeah. So this is our final network, 2R and 2R. Now it is here, right? Because 2R, 4R, and this branch is also 4R. This is 2R. Smaller and capital R. I have made a distinction. Therefore, this 4R and 4R parallel means 2R. So I am again writing this. So 4R and 4R. Therefore, this is 2R. And this one is 2R, smaller. They are in parallel. That is our final answer. So now here you will use two resistors, parallel combination, R1, R2 back, R1 plus R2. Therefore, this is 4 capital R small r by 2 into R plus R. Right? So this is our result, 2 capital R small r by R plus R. Now I have told you the point of common potential points. Right? In the next example, I would like to show that common potential points as a solution. 12 identical resistors forming a cube. 12 identical resistors forming a cube here. The same frame can also be shown as a different geometry. This and this both are identical. Afterwards you can zoom and you can please see both are one and the same. Even I have marked all those corners as well. A, B, C, D, E, F, G, H. All the corners also I have shown here. Now the question is, here in this case there are three possibilities of a question, that is, find effective resistance of this network across the longest diagonal, or else effective resistance across phase diagonal, and the effective resistance across adjacent coordinates. So these are the three ways of asking a question. Now here you see, supposing I want across body diagonal, what does it mean? The longest diagonal. In this case, it will be this corner B and this corner G will be the longest diagonal. So now I want to calculate R across BC. And for this purpose, I show that method of common potential points. Remember, all are identical, each of capital R. I have not mentioned here, you can take it for granted. Identical, 12 each R. Now here I take a current entering at B because we are finding across B, G, open terminals. Supposing current entering at B and leaves at G, therefore it's again 3I. In such case what happens? See, this 3I, again 3 branching are possible. B to A, B to C and B to E. Because of the symmetry, current splitting should be identical. Therefore, 3I, I in the branches of BA, BE and BC. Therefore, what does it mean? P, this, use V is equal to IR for BA, BC and BE. Then VBA is equal to VBE is equal to VBC, because all are at same potential points. Therefore, now A, E and C becomes common potential points. Got the point? So now I can say 1, 2, 3. These three resistors are parallel across. See, this is the terminal B. Then the three branchings I am showing 1, 2 and 3. Let me also show this. Now what is this point? This is the point, you can say, this is the point, you can say A, comma C and also E. This is single point, common potential points. A, C, E are all common potential points. Similarly, at the end G you will find. Similarly, look at the end G. End G also again. I and I, all the three currents are adding at G. Therefore, the PD across GD, GF and GH are also one and the same, because of same V is equal to IR. Therefore, now which are those 3 points from G? This is D, F and H. So this is another point I am taking. This point is nothing but point D or point F or point H. Point H. Therefore here you will find 3 more resistors. We'll find 3 more resistors. 3 more resistors again. R. Right. So how many has gone? So now it is like 3 plus 3, 6. Another 6 resistors are there. Now what we find is that this current I in the branch AB will again split as I by 2 and I by 2. Right? This I also splits into, yes, I by 2 and I by 2. Again, this I also splitting right to I by 2 and I by 2. Therefore, how many total resistors are there? 6 resistors, each carrying a current of I by 2. Therefore, all those 6 resistors are now parallel. Identical splitting taking place, all are in parallel. Therefore, now I will show these are the points. Please do remember A, comma C and E. Now I am showing 6 more resistors. 1, this is 2, 3, 4, 5 and 6. Each of capital R, of course. Now this is how we have identified the common potential points. Last example, it was easier in very short time we have found that common potential point, whereas here we have needed 1 or 2 more steps here to find that. That is why in the previous example we can directly use Kirchhoff's laws, but to understand the concept of common potentials in a simpler way, I have used that method. Now here you will find a simple answer. Why? Because these are 3 resistors in parallel. It becomes R by 3, and in between these common potential points, it will be 6 resistors in parallel each of R. Therefore, this becomes R by 6, and also at the other end you have R by 3. So R by 3 and R by 6. Got the point? R by 3 and R by 6. It will give you 5R by 6. The effective resistance across the longest diagonal or BG is equal to 5R by 6. Please do remember, here I have shown the current division. This will also be helpful, and you can directly find your answers. Supposing in this kind of network, I have shown like ammeters. One ammeter, I call this ammeter A1, or somewhere over here. See, another branch somewhere. Somewhere I will show like, yeah, here I will show one more ammeter, A2. Now what are the values of A1, A2, A3 likewise? Or else it is across, where is that B? Yeah, across B and across G, one ammeter is connected like that. So what is the answer for that? I have earlier told you, whenever ammeter voltmeters are given, we have to first find circuit current. So what is that circuit current? Circuit current I is total volts across, supposing I ask BG, total volts by total ohms, which is nothing but 5 R by 6. So this is 6E by 5R, which is the, yes, which is the circuit current. This circuit current, what we have found is splitting equally in the branches of BA, BC, BE. You remember that current splitting in the branches. Therefore now, if it is asked between, see, this A1 is between A and D. Find here, where is that A and D? This is A and D. Supposing if I call this I, this will be I by 3, I by 3, I by 3. This I by 3 splitting in the branches AH and AD. Therefore, this is half of I by 3. This is I by 6 and this is I by 6. Right? So, what are the now possibilities of ammeter reading? The ammeter readings are, it is either I, which is 6E by 5R, and that ammeter reading will be 6E by 5R for the ammeter connected between B and G. Whereas, now for any other thing, what are the other possibilities? It is either I by 3 or I by 6 are the ammeter readings. I hope you are understanding this. We first calculate the circuit current and then circuit current being split. The three possibilities are I by 3 and I by 6. Where I by 3, where and I by 6 we have shown in details. Please go through this example. The same kind of common potential point, supposing if I apply, I will write 2 more results. I will write 2 more results and I ask you, please do remember it. We have done one in detail. So the other 2, I will show the results. Now I am writing R across BD. This BG is nothing but body diagonal. BD becomes phase diagonal. So I call it as across phase diagonal. Across phase diagonal, same kind of strip, and will give you the result RBD is equal to 3R by 4. I said BD, need not be BD, any phase diagonal, the result is 3R by 4. And also one more, I am writing, supposing if it is BC. BC, what does it mean? Adjacent corners, right? It is adjacent corners. Any adjacent corners such as BC, or it may be CF, or it can be AD, anything like that. Adjacent corners, effective resistance RBC, adjacent corners is equal to 7R by 12. See. So based on this common potential point, we have done one example. There you can find 3 to 5 examples, finding ammeter values or finding effective resistance across different. Only 3 possibilities are there here for 12 identical resistance forming a cube, phase diagonal, body diagonal points and adjacent corners. Now look at this network. This is the given question, and the question is, for this network, find VA minus VB. Or else it can be a question like A at higher potential, B at higher potential, or both are at same potential, such options. Even a question like that is also possible. Now in this example, you are asked to find VA minus VB, right? And actually here, this 10 ohm resistor is there in the network, which we need not use because we are talking about these terminals A and B. See, I have redrawn this between X and Y. 10 volts of potential difference is applied. Now this is the one which we have discussed in last class, the Wheatstone network equivalent R1, R2, R3, R4, and between this A and B, in fact, we have connected the bridge element. Earlier we call it as R5. Now here there is no R5. So that is the only difference. Now for this network, I would like to remind you an important result that we have done. Otherwise, it will be a lengthy procedure to do it in a short time. I am giving you this result. Already we have given that. Hope you will practice it. VA minus VB. Order is important. I am writing the expression for VA minus VB is equal to total volts times R2, R3 minus R1, R4. R1, R4 by denominator term is R1 plus R2 into R3 plus R4. This is the result. Now a small substitution. The total volts are 10. What is R2, R3? 2 times 2, right? 4 minus 3 times 3, 9 by R1 plus R2 into R3 plus R4. Both are 3 plus 2. The 5 into 5. So here, this is minus 5. Remember, minus is coming and it carries an important point. Therefore, what is that final answer? 10, 25, 5. This is minus 2 volts. Minus 2 volts. What does it mean? Of course, we got the answer as 2 minus 2 volts. What does it mean? A is at lower potential and B is at higher potential. Supposing if there were any bridge element, the current will be from B to A, not from A to B. So this is what the principle that we have used in the case of Wheatstone network. Now one more example. Let us continue the same concept of Wheatstone bridge. Hope you got the answer for this, right? Now you see the next example. The next example is straightforward question because this is what is a very famous network that we have seen. 1, 2, 3, 4, 5, you remember? R1, R2, R3, R4, the order and all. Now here, this is the current I entering at this node and leaving at this node, he says. Now he says the current through branches, this current through 100 ohms is I1, through this 25 ohm is I3, and at this branch, the current through 300 ohm is said to be I2. Now the question is, compare I1, I2 and I3. I want the comparison only, increasing order, decreasing order of currents. That is what is needed. Now whenever such network is given, first you verify for the condition. Remember, in the case of Wheatstone network, you remember this, R1 by R2 greater than, R3 by R4 less than, and the balancing condition is R1 by R2 is equal to R3 by R4, we have said. So first you check or verify for that condition. Then this is R1, R2. R1 by R2 is 1 by 2. R3 by R4 is also 25 by 100. Same 1 by 2, right? So here the condition is satisfied, balanced network. Therefore this 300 ohm is ineffective. What does it mean? No current through this. Therefore I am now writing I2 is equal to 0. So one volume done. Now how to get a comparison between I1 and I3? That is, this I1, now there is no 300 ohm, you will remove this. Therefore this is I1, current in this branch, In this branch the current is I1 where the total resistance is 300. Whereas what is I3? I3 is in this branch. So this is what is the branch where 25 and 50 ohms will be in series. Therefore what do you observe here? This current is I, now splitting into two parts. In this branch the total resistance is 300 ohm and in this branch the resistance is 75 ohm. This is what is I1 and this is what is I2. We know that current division in the inverse ratio of resistance 300 ohm, higher resistance 75 ohm. Therefore, here what do you observe? I2 greater than, so this one is I3 given in the question, right? So therefore, we see I3 greater than I1. And also what you find is 75 and 300 means it is 4 times. Current, resistance 4 times means current is 1/4. Therefore, if you write it as an equality also, I3 is equal to 4I1 because the resistance is 75 and there the resistance is 300 ohm. Therefore, I3 is equal to 4I1. So finally, what will be the ascending order, descending order, inequality, whatever you write? Then it is I3 greater than I1 greater than I2. And of course, this I2 value was 0 because of the balancing condition. Likewise. So generally, whenever we are given networks in the CET and NEET examination, most of the times it will be like a Wheatstone bridge. That Wheatstone network, we have shown a post office box. In fact, the same post office box, if it is changed, it will be seen as a different geometry. The bending of wires is different. The same I have done in my next example. See, the next example, we don't find it the post office box and appear to be completely a new or different one. Here, there are 1, 2, 3, 4, 5, 6. Generally, we do follow that there are only 5 resistors, R1, R2, R3, R4, R5, and we check for the conditions. Need not be there, let there be more number also. But in the deduction, we may or we will get or we may get the 5 or 4 number. Here you will not find this 2 and 3, nothing but 5. Therefore, I am redrawing here. This one is 5 ohms and this one is 10 ohms. This one is 10 ohms. And here also this one is, yes, this one is 4 ohms and this one is, you will find 12 and X in parallel. Actually the question is for what value of X ammeter shows 0 reading. Ammeter showing 0 reading means there is no current through ammeter, right? We will make that point for our balanced Wheatstone network. Now here is the ammeter. Here is the ammeter. Now this is X and this is 12. 12 and X. Suppose I call it as R. R value is 12 into X by 12 plus X, the parallel combination. And now it is nothing but the same, right? Now this is how we have redrawn. So once again, it is A, B, C and D. BD becomes the bridge elements and PD across AC. Therefore, it is the same Wheatstone network now. Wheatstone network, for the ammeter to be 0, it should be a balanced bridge. So what is the balancing condition? R1 by R2 is equal to R3 by R4. So what is R1 by R2? 5 by 10. Therefore it is 1:2. Therefore it is 4 means R should be double. See, 5 2s 10. Therefore 4 2s 8. Therefore the condition now I am writing, it is 12x by 12 plus x equal to 8. Solve it. You will get x is equal to 72. The section 72. Yeah, 24 ohms you will get. X equal to 24 ohms you will get. Right? Because of the popularity of Wheatstone network, I will show the Wheatstone network which you have shown in the post office box in the other forms as well, so that as soon as you look at the question, you will understand that it is a Wheatstone network. How? It's a simple thing. Not any such shortcut or not any such blindfolds. Here what you find is across the terminals AC, open, potential difference applied, BD bridge element is there, which you will write it as I phi. Now here you see, supposing this is A and this is C. A, yes, connections are from R1 and R3, therefore this becomes R1 and this one is R3. For C it will be like R2 or R4, right? Then it is nothing but this becomes R5, like that. Next one also the same, but a bending of the wax is different. Now you see again, if this is A, I will let it as C, A connection for R1 and R3, suppose I write C, A, R1 and R3 common point, like this. So identify common points and mentioning here. For C also what you observe, R2 and R4. Now the point is that which one is R2 and which one is R4 should not be confusion, because R1, R2 has a common point B, therefore if this is R1, this should be R2 and hence this one is R4, naturally this becomes R5. Now how to find those points B and D? Look, B is the common point for R1, R2, R5. R1, R5, R2, therefore this point becomes D and this point becomes, this one is B and this point becomes D. The common point for R3 and R4, R5, this is B. So it is one and the same. It's only the difference of bending of the wire. See, one more way I have changed. One more form I have changed. Supposing if I call these as A and C, these are the open terminals A and C. Now you only write all those R1, R2, BD points and all. Supposing if I call this as R1, this should be R3, right? Because common point A for R1 and R3. If this is what is R1, C. Now what for C it is R2 and R4. Therefore this will be R2 and R4. Why this one is R2? Because R1, R2 has a common point. That common point is what is B, and R3, R4 the common point is D. Therefore between B and D the bridge element, now this becomes R5. Like that. It's a simple change of geometry. Same I have shown this way also, bending in a different way. See, supposing I call these terminals as A and C. This again the rule goes R1, R3, R2, R4 and this becomes R5, like this. Supposing if it's straight away given, we'll write the answers, and in all these cases do remember, most of the times when I say 99.9% we are given the balanced bridge, and for the balanced bridge the condition of course R1 by R2 is equal to R3 by R4, or it is R1 by R3 is equal to R2 by R4, whatever, but the order is important. I have number of times mentioning you, and in this case if this condition is satisfied, then what is that RAC, the effective resistance would be R1 plus R2 times R3 plus R4 by R1 plus R2 plus R3 plus R4. See, this is our simple expression. Any of such forms given, you will find. Supposing all are identical, R1, R2, R3, R4, all are identical, condition is satisfied, then if I substitute all these values, then it also be R only. The effective resistance is equal to one of the resistors in the branches, like that. But the same asked in a different way. Supposing I now frame a question. Look at this example. Here I have shown you one Wheatstone network, right? Let me now put a question. This is a network. Yeah. Now he says all are 10 ohms. This one is also 10 ohm, and here he says this value is R. Now the question is, this question, what is the, so the asked question is, for what value of capital R the effective resistance will be 8 ohms. 8 ohms. Now here, just now we have shown that this entire marked region, you see R1, R2, R3, R4 and R5. That forms, yes, Wheatstone network. In that Wheatstone network, the condition is also satisfied, therefore it is a balanced Wheatstone network. In the balanced Wheatstone network, just now we have mentioned that all identical resistors, each of R effective will also be capital R. Right? Just now, couple of moments back. Therefore, this R effective will be 10 ohms and this one is capital R. Now, both are in parallel across AB. Therefore, now 10R by 10 plus R equal to 8. That's the answer, right? So 80 plus 8R is equal to 10R and R is equal to 40 ohm. R equal to 40 ohm. So it is nothing but Wheatstone network which we can identify, and for that reason only I have given you in 3 to 4 different geometric shapes. Now few examples on EMFs and cells. First one, to begin with, a small network is given and it says for this variable resistor, this one is variable resistor, for this variable resistor circuit, a graph is plotted between voltmeter and reading versus ammeter reading, and this is what is the graph. I given to be in amperes and volts given to be in V given to be in volts. Now the question is, find the EMF of the cell, find internal conductance of the cell. Just for a small change, generally we do write internal resistance small r. In the last sessions we have seen the reciprocal of resistance is what is called as conductance. Remember the unit? Siemens, ohm inverse, mho, like that. Now, the solution is, as I have told you, whenever cells are given, we begin with our relation of terminal voltage V is equal to E minus IR. Right? V on x-axis, and now you can see I on x-axis. So shall I compare this with the equation y is equal to C minus mx? Y is equal to C minus mx comparison. Finally, you will get your answer within no time. Now this C is the y-intercept. So this y-intercept is nothing but the EMF. Remember, V is equal to E for I is equal to 0, PD across cell in open circuit. Therefore, you compare these two, what do you get? Now EMF is nothing but y-intercept. Y-intercept, look at that graph. What is that y-intercept you got? 5. Therefore, EMF of the battery is equal to 5 volts. Then what is the x-intercept? The x-intercept is nothing but now x-intercept is, look at this, y is equal to C minus mx, and what is that x value is nothing but I, because x-axis calibrated. Therefore, what is that x-intercept? This is what is I current, and therefore comparison will give you slope. Slope is equal to M is equal to negative of capital R, of course. You can see this is a straight line in first quadrant with negative slope, and that is why you have this minus one here. So slope is equal to resistance. If I take magnitude of slope, then magnitude of slope gives you the magnitude of resistance. How to calculate the slope? The slope is equal to dy by dx. So slope value is 5 by 2. So this is 2.5 ohm. But don't stop here. It is asked for internal conductance. Therefore, our answer is 1 by 2.5, 0.4 Siemens. 0.4 Siemens. Like that. So cells, whenever question is given, most probable will be like terminal voltage V, EMF E, and we have told IR is the last volts where R is the internal resistance. We have talked about different cases of that V is equal to E minus IR. Right? You got it. Now, one more example. Same concept of V equal to E minus IR. E minus IR. Look, this is the question. The question says P and Q are two cells of EMF, each capital E, but internal resistances are R1 and R2. Now this combination is connected to an external circuit of resistance capital R. Now the question is that find R such that PD across the cell P will be 0 is the question. Now look here. It's all in a closed circuit, therefore PD across P is nothing but terminal voltage across P. If it is PD across Q, it is a terminal voltage across Q. Therefore, we are using V across P is nothing but E of P minus R, I, which is the current drawn and current in the circuit, times R of P. R of P, because we are calculating PD across P. Now according to the example, this is going to be 0. This is going to be 0, and what is the value of EP? Said to be E minus I. I is the circuit current. See here, this is the current direction we will draw here, because everything in series, no question of any current division. I is the circuit current, so circuit current is always total volts by total ohms. Now, total volts. Remember, series of cells, opposition in series in opposition, parallel combinations, all discussed in the last class. If you now here, these two cells are said to be in series. Why? Because negative connected to positive and so on. Therefore, I am writing total volts E plus E. Right? Therefore, I will write it as 2E. And what is the total resistance? R1, R2 and R all in series, therefore R1 plus R2 plus capital R into what is that RP? R1. This value is 0. Simplification, yes, E term is gone. R1 plus R2 plus R minus 2R1 equal to 0. Therefore here capital R is equal to R2 minus R1. You got it? Right? Remember, we are finding PD across the cell P and it is said to be 0. Then the value of capital R is R2 minus R1. For the other case, it will be like R1 minus R2. So whenever cells are given, the popular topic would be V is equal to E minus IR. When I am writing this V equal to minus IR, let me tell you one important principle regarding cells. The question I will frame like this. This is a cell, 2 volts and internal resistance 0.5 ohms connected to an external circuit of resistance capital R. Now the question is, for what value of R current or maximum current can be drawn from the cell, or find that maximum possible current in the circuit. Now this is called maximum power transfer theorem. We don't give any proof, we will give is the statement. In this case, if this is what is EMF E and internal resistance R, condition for maximum current is for capital R, which is the resistance of external circuit, which can be varied but not smaller. Generally, for a given cell, internal resistance is an internal matter, therefore we can't adjust it. Therefore, here I am getting the condition for maximum current, resistance of the external circuit is equal to internal resistance of the cell. Capital R equal to small r, current is maximum. In such case, what is that I we have written earlier? Total volts by total ohms. It is E by capital R plus small r. For capital R is equal to small r, we are now writing I maximum is equal to E by 2R. E by 2R. Therefore, in this given example, R is equal to 0.5 ohms. Therefore, I maximum is equal to 2 by 1, that is equal to 2 ampere. Once you got this current, even it can be asked what is the maximum power, that will be I square or likewise. So V is equal to E minus IR and maximum power transfer theta. Yeah. See, this example says 3 identical cells, each of EMF E and internal resistance small r, 3 identical, deliver same current when they are connected either in series or in parallel across an external circuit of resistance capital R. That is, first time all the cells connected in series and then connected to external circuit. Then current. Afterwards, all the cells are connected in parallel and then connected to external circuit. Then the current. Both are same, he says. Now the question is, find small r by capital R. For what ratio of small r by capital R, this condition will arise, current being same. Now it is said that IS, in the series combination of cells, is equal to current due to the parallel combination of the cells. And we know how to write the current. Current is total volts by total ohms. First, let me write it for the series combination. For series combination, yes, current is total volts. Now, how many we have taken? Supposing n we have taken, in the given question that n value is 3. Let me now write it for a general expression. N cells identical, each is series. So, what will be the EMF? Yes, it is NE. And what will be the resistance? Each are n such in series. Therefore, this is n times small r. And of course, external resistance of the circuit is capital R. This one. Next, let us write it for the case of parallel combination of cells for the same external circuit. Then IP. We know that parallel combination of identical cells, no change in EMF. The combination will have the same EMF as that of a single cell. Therefore, it is equal to E. And now what about the resistance? Each small r, n such number parallel. Therefore, it is R by n. And of course, resistance of the external circuit. Simplification, I will write it as NE by small r plus NR. Now, the example says they are equal. I will equate them, right? NE by NR plus R is equal to NE by small r plus NR. Very easy simplification, you will do it. So then you will get it as capital R is equal to small r. That is, for the ratio capital R by small r equal to 1. Now this ratio is 1. For such case, this condition will arise, same current in series and parallel combinations.